Okay, so I'm going to talk about Half-Life, but I'm not. I want to include a brief kind of overview of radioactivity at the start, just to make sure that it's all clear. Essentially, what radioactivity is, or what nuclear decay is when something, an element we can call X, is going to decay and to change into a different element which we're going to call Y, and then it gives off some radiation. So the nuclear radiation is the stuff that is given off. In order, if X can decay into Y, then we would have to say that X is unstable. Now, there might be, if this was, for example, let's do an example. In fact, yeah, let's do an example. Let's do carbon. So carbon has a mass number of, atomic number. I'm going to do the atomic number at the top. I don't know if it's always at the top, but it can change anyway. Now, because it's got an atomic number of 6, it is carbon. There's no such thing as any element that has an atomic number of something other than 6 that is carbon. And all elements that have an atomic number of 6, or all atoms that have 6 protons, are carbon atoms. But this particular carbon atom has a mass number of 14. Now, if you look in the periodic table, it will say 12 or something around about 12. So this is a bit of a strange version of carbon. There are other versions of carbon, other types of carbon, such as this one, and the more common one, that one. And then you even have this one, I believe, and possibly this one. We're just going to be looking at this one. Now, all of these, they're all carbon, but they're clearly not the same. So they are isotopes of carbon. Okay, so I like to use the word type, as in rather than kind or versions of carbon, because you can think of isotypes or topes. You can think of like as types, though the word is isotope, not isotype, but might help you to remember a definition and understanding what isotope means. So we can't say this is a mistake that people make, as they might think, well, which one's the isotope and which one's the normal one? That question doesn't make any sense. We can say this is the most popular one, or the most abundant one, the most common one, and we could say that this one is unstable. So, but the other ones are actually not unstable. I don't think they are anyway. This one definitely is. So when we say this is unstable, we could also say, because there might be other isotopes of X, this particular one is an unstable isotope of X. So this is why the word isotope gets thrown around in this way. Now, Y may or may not be unstable. We don't know. If it's unstable, it could decay again and produce something else. But so we'll do an example of this decaying. So we're going to take a carbon-14 isotope, and eventually, if we wait around long enough, we will see this isotope changing into nitrogen. And the mass number is the same. The atomic number must be 7 because otherwise it would not be nitrogen. So this is a bit strange. And in fact, this type of the strangeness of this needs to be recognized. So we'll look at what I mean by that in a moment. But they really want you to notice that it's strange. So we're going to see if we can see and identify this. What do I mean? Why am I saying this is so strange? Well, so let's say that's going to be my symbol for proton. This is my symbol for a neutron. And we're not interested in the electrons around the outside. We're just going to be doing the nucleus. That's why it's called nuclear physics, because we're just looking at the nucleus. So we have 6 protons. And we have a mass number of 14, so therefore we must have 8 neutrons. So let's put all this together now. I'll pause the video while I'm doing that. Right, so there's my carbon-14 nucleus, and it's going to decay into nitrogen-14. So it's still got 14 things. So let's just copy this for the moment, and we're just going to edit it to make it correct. At the moment, this is just carbon-14, but we need to work out how to change this diagram to make it nitrogen-14. Still 14 things, but it's got 7 protons. And so it must have 7 neutrons. So actually all we need to do is take one of the protons, maybe this one up here, and change it green. And now I think we have... oh, wait, no, it doesn't. That's the wrong way around, isn't it? So I want to take the neutron and turn it into a proton, don't I? Let's take this proton, sorry, the neutron, take the neutron down the bottom right, turn that into a proton because it's got more protons now. It's got 7 protons, and therefore it's got 7 neutrons. So actually, that's actually, in fact, what did happen. This neutron did, in fact, become this proton. And like I said at the beginning, we have some radiation given off. The radiation, this type of decay, is beta decay. So the radiation is called a beta particle. And on closer inspection, it turns out that this beta particle is in fact an electron. So, and as I said, what they really want you to notice is what's weird about this. So why is it weird that we have this electron? Well, it's weird because there was no electron there in the first place, and now suddenly there's an electron. And on top of that, how did the neutron just become a proton? So they want you to realise what's actually happened there, and accept that that is what's happened. This electron has not come from some orbiting electron, from the electron. It's not come from the electron shell. It is from the nucleus. A neutron changed into a proton and an electron. And this electron has a lot of kinetic energy, and so it flies off and is emitted from the nucleus. And it's ionizing, which means it can cause cancer and radiation poisoning and so on. So that's the radiation. Now, so we'll leave that there because I don't want to talk any further about that because I want to now just talk more about half-lives. So what we'll say then, instead of drawing all of this, I'm going to just do a black circle with a C in the middle.
Which phone number, contact or device do you want to...
Sorry, Alexa just came alive. So let's... Okay, I think what's happened there is I've written 2 C's. Yeah. And I'll just make them a bit bigger and then I'll delete one of them. So that is now that represents this, okay? And then I'll do another circle for nitrogen, and we'll do that in blue. And there we are. So that one represents that. So we could do an arrow. So it could be, we could, okay then. Basically, we can do that. All right, so let's say we had a bunch of these. Okay, I'm going to make a little grid of these. Okay, so I made a grid of 4x4, so we've got 16 carbon atoms there. Now, we can't ever predict when a carbon atom is going to decay. So this carbon atom here is going to decay at some point, but we never know when it's going to be. What we can do, however, is we can for complicated reasons, there is a certain probability it will decay within a certain time. So this is a weird way of defining half-life, but I like to define it in this way as well. But essentially, the half-life of carbon, which can be written as this, carbon-14, I think it's 3,600 years, but I'm not so sure anymore. I'm just going to check that. Half-life of carbon-14. No, it's not that at all. It's 5,730 years. So, not that you need to know that number anyway, but it might as well be accurate. I'm just going to get a link to this. So, after 5,730 years, what does that mean? Well, for any one of these atoms, there's a 50% chance that they would have decayed. And so we can sort of say, and this is grossly oversimplifying, but we can sort of say that half of these atoms would have decayed within 5,730 years. Now, in actual fact, that doesn't quite work, because let's think about it like this. We know there's 50% chance of flipping a coin and getting ahead. But if you flip a coin 10, you can expect, if you flip a coin 10 times, you can expect you're going to get 5 heads and 5 tails. But it would be silly to say that you're definitely going to get 5 heads and 5 tails. However, if you flip a coin 1,000,000 times, then you can be fairly confident that you're going to get roughly 500,000 heads, 500,000 tails. So it's not going to be exact, and for smaller numbers, it's much more noticeable. However, let's say in a perfect world, it works out. So the definition, really, that you will have been given, and this is, I want to start off with the terms of probability first, because it can be a little bit confusing. You would have thought this would always decay to half of that. Okay, I'm jumping ahead here. So basically, half-life is the time it takes for half of a sample to decay. Now, what do I mean by sample? I just mean, in this case, it's those 16 atoms, 16 nuclei. So it's it doesn't really matter. I've just taken some carbon and I'm asking questions about it. The carbon that I've taken is the sample. That's all that means. So we've got this decaying. Well, nothing's happened to it yet, according to my diagram. So I'm going to change this. Now, the mistake, that's what some people make. Is they just take a bunch of these and they delete them like that, which seems like it makes sense. And then a second, I need to delete one more. However, this means that the rest of them have just disappeared, but they didn't disappear, did they? They changed into nitrogen. I'm actually just going to make it just like this. I'm just going to. I'm going to delete them, because I've got to write N on all of them, haven't I? Probably should have just given them just unlabeled. It would have been a bit easier. Never mind. Okay, I'm going to just pause the video and set them up now. So there you go. So after 5,730 years, 5,730 years, we're going to have that situation. After another 5,730 years, it of course doesn't. We don't. What some people might think is they all go. The other half goes. No, it's half of what we've got again. So now it's down to that, right? And if we go again, we go down to that. We lose another 2 carbon. We half it again. Okay. And then you do it again. It'll go down to 1. Now, remember though, that this is it's not really likely to do exactly that, because this is just it wouldn't work like that with small numbers. But I don't want to go too much into that at this stage. So pretty much it does that. So now let's look at let's think about the radiation that's been given off. In the first 5,730 years, it would have given off 8 beta particles. But in the next one, it would have only given off 4 beta particles, and then the third one, it would only have given off 2 beta particles. So, so we can see that. So the amount of decays that are happening and the amount of radiation that's given off, that's known as the activity. So the activity is the amount of, let's say it's how often decays are occurring. And you can measure the activity by using a Geiger counter, because the Geiger counter detects the radiation. And if there's a lot of radiation, there's a lot of activity. So, and as we can see, as the amount of atoms halved, so did the activity. So another definition of half-life is the amount of time it takes for the activity to halve. So you have these graphs. I'll demonstrate. I'll quickly get a graph. So you have these graphs like this: number of nuclides. That's just another word which I don't think you need to know. It just means nuclei. I'm not sure why it's using the word like that. So don't worry too much about what these numbers mean, but essentially after one half-life, so T-half is just a symbol for half-life. After one half-life, it's halved. After 2, it's halved again. After 3, it's halved again, and so on and so forth. And so it's got a table down here that kind of demonstrates it. It looks like they're kind of demonstrating how it fluctuates a little bit. Not brilliantly, but I guess they're rounding up at some point here. Anyway, so what you'll also see though, and this doesn't come up very often, but let's see if I can find a graph to demonstrate. Actually, I'm going to run out of time. But what you'll see is that in some cases, it doesn't approach 0, it approaches a number above 0. And the reason for that is because your Geiger counter is detecting background radiation. And so even once your activity of the sample has totally dropped down to 0, it's still measuring some background radiation. And so that would have to be subtracted from your data to get a more accurate graph. So I think that just about covers it. So I'll stop the video there.